Okay, so now back in Houdini we will start to create those vector attributes that I was talking about earlier. So the place where we will be adding those is in between the drag and the split, so that any attribute that will be applied to the parent attribute can be sort of inherited by the child attributes at the split. So the first attribute that I want to go and hunt down will basically be the last good velocity. So if I just sort of bring up my spreadsheet for that particle, then I can go and look for the velocity in x, y, and z. So there's my velocity, right? Now the particles at the moment, this particle will just keep going, and that's just fine. It will, since there is a constant force to it. Now if I just disable that force just for a second, just disable this with disable bypass flag, and I let it play, then you will see that after a while, this particle will basically start to slow down until there is almost, see over there, Vx from particle 0, Vx, Vy, and Vz. The particle almost has got no velocity anymore. So as you can see over there as well, it's just slowing down, there, until there's almost no velocity left. At this point, the vector of the velocity will be almost, completely zero. If at some point the particle would stop, we would have a problem calculating our cross product. So we want to make sure that we sort of measure the length of the velocity vector and check if it is higher than a certain number or lower than a certain number. And if that is the case, then use the previous one. So let's put in an if statement. But we first need to create a new attribute. So under the drag, just say attribute there, and I'm going to name this guy last good velocity. So the kind of attribute that I need will be a vector attribute, and I'm going to call this LV, very short, last velocity. In the values, I'm going to, like I said before, gonna start writing an if statement. What I want to check is the length. I want to check the length of the velocity vector. So I'm going to start typing the expression length, and inside of length I will start to type my sort of components of the velocity. So Vx, Vy, and Vz. So these components are now going to sort of tell me the entire length of my velocity vector. And I want to check this and say if it's smaller than, well, we'll just put in the start value, sort of like 0.5. So if the velocity, the complete length of the velocity is going below 0.5, then I want to use whatever the previous value of this guy was. So the previous value of this guy is $LVX. So LV is the name of the attribute, and X is the X component. So say in the beginning, this component will be 0. So if the velocity is really small in the beginning, then it will still be 0, which will give a bit of a problem. So we will need to give it an initial boost of force, which is happening in the sort of location birth. Now generally you do expect in the beginning there would be a bit of force, so that's fine. And otherwise, if the velocity vector is higher, so if it's traveling at a high speed and changing direction, whatever, then we do want to use this new velocity vector. So then we want to use the velocity. Otherwise, use the old one. Okay, since this is a vector value, we need to apply this to all the different channels. So at the moment it's just applied to Vx, or LVx, which is the X channel, the X component. So if I select this entire thing and copy paste it into the Y channel, then I need to make sure that I change my settings to LVY and using Vy. Now I don't need to change the length, because that uses all the components, so that can stay the same. Alright, and once more for the Z component, so just change the Z components of the sort of the last good velocity and then the velocity. Okay, so if we have a look at this now, then we can see at some point, if the velocity vector is smaller than 0.5, we can kind of start to see that the velocity will be maintained. So if I bring up that spreadsheet, so let's have a look. There's my velocity, and at some point you'll see in the beginning it's changing, and at some point it should stop changing because the velocity vector should be too small. Well, my new velocity vector rather, so LV, yeah, there. So at some point it's going down, and there we go, it just stopped, yeah, whereas the velocity is still updating, there, the velocity is updating my newly calculated velocity, because the next step would have gone under 0.5. So now I've got basically a vector, so 0, 0.5 and 0, which I can start using. Well, I can't start using it straight away because a 0.5 as a maximum value is not very useful. So what I will be doing now is basically normalizing this vector. Yeah? So I'm going to add a new attribute underneath this. I'm going to kind of split it up a little bit in these attributes. And I'm going to call this one veloc. Yeah? So just to indicate this is the kind of velocity that I will be using. So veloc, there again, velocity. Again, it'll be a vector value. And I want to normalize it. So normalize, open, and I want to use my vector3 data type. Again, if you're curious about any of these expressions, just go to Windows, HScript, bring up HScript, and xhelp, and you can find all of them and whatever they mean. And we'll kind of show different noise types later on for the volume, but this is where you can find it. So just type in textport xhelp, and then you can kind of type in normalize or vector and see what they do. Okay, so vector3. So the first component will be lvx. The second component will be $lvy. And the third component will be $lvz. So this vector will now be normalized. Now the only thing to keep in mind again is, since we're dealing with the first component, is that we need to add that little, that little sort of indication flag of which component of the vector that we're using. Then again, I'm going to select the entire expression and copy it so that we can use it in the Y channel. And the only thing we need to change there is change this to 1. Yeah? Again, change it once more into the Z channel. There, and the component is 2. Okay, so if I look at this guy now, and I'll just rewind my particle system, play it again, always need to do that, and let's have a look at our spreadsheet. Yeah, and if I look at my veloc, now you can see 0, 1, 0. Now this is quite useful because now we can start to use this into our calculations. Which calculations? Well, the first thing we will start to need to do is basically find out the dot product. So find out if if I can actually start calculating my cross product, because I say if at the moment, if my velocity vector going straight up is sort of corresponding with my position of my particle, so I'm going to use my position as a vector, then we're going to have a problem. So in order to do that, I need to use a dot product to calculate the different. So I'm going to use yet again a new attribute. Now a dot product will return not a vector value but a scalar value, and I'm going to quickly name this dot, and I'm going to call my attribute dp for dot product. dp, so a float, that's fine, and the value that I'm going to be calculating now is going to be the dot product. So first of all, I need a dot product in there. I need two vectors. The first vector, vector3, will basically be that velocity. I don't need to normalize it. So that velocity that I've calculated there, I don't need to normalize it because I normalized it in this step. So if I add it in there now, I can just use $veloc. You could put all of this sort of in one huge expression, but yeah, that's gonna become a really bit difficult to find out and to change otherwise as well. So we've got $veloc in Y and $veloc in Z. Veloc Z. So that's the first vector. Now I need a second. So the first vector of my dot product is in there. Now I need a second, which will be again a vector3. And in this case we're going to be using the transformation. So $tx, $ty, ty. It's kind of going off screen. So if this expression becomes too big, you can just press Alt E, and this will bring up an expression editor which will allow you sort of to type in bigger expressions, so $tz in there. Now there's one more thing that will happen, basically, is that if the angle between, say, this velocity vector and this transformation, this position vector, and this is a 3, not a 4, if this vector becomes sort of the angle between the two is going over 90 degrees, then this dot product will become negative, and that's not something we want. So in order to avoid it becoming negative, we're gonna put an absolute. So basically get the absolute value of this floating, this float. Dot product will return a float between 0 and 1. And we want to get the absolute value. Now one more thing that we will have to add as well is we know that this one is normalized, but this one, well, we don't know if this vector is normalized, so we're gonna add a normalize to this guy. So normalize, this vector, like this. So now I've got two normalized vectors. This is normalized, and this one entirely is normalized as well. I calculate the dot product between 0 and 1, or rather between -1 and 1 at this point, and then I add the absolute to make sure it goes between 0 and 1. Okay, that's fine. So say apply and accept. Oh, was there a little... Let's have a look. It should be calculating this. Let's rewind this and let's have a look if it does it. Spreadsheet. So the dot product at the moment is 1 because they are overlapping. So let's bring in that force again to kind of, so this would be a problem if we would just be using those two. So let's bring that force again. So now they're kind of, it's going to be offsetting, and we can see the dot product at the moment, since like I was kind of predicting the scenario of him going straight up and then he's going to curve away, and the more he starts curving away, the lower this dot product sort of becomes, until at some point it's sort of going to be so far away from the origin that the origin and the velocity vector will almost line up again with one another. So you'll see this vector will start to decrement. So it's going down, 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 and as it goes away from the origin, you can kind of see it curve off. So we've got the velocity vector going in that way, and we've got the position vector, so this position vector, sort of there, and velocity going that way. So you've got this plane between this one and that one. And so these values are good. This will define a plane, so we can start using this to calculate our cross product with. So the next thing that we want to do, what if this vector, or rather what if this dot product is actually 1? Then we want to define a custom vector. So how do we define a custom vector? Well, an easy way of sort of defining a custom vector might be by adding a point in subs that will give us information wherever the point is for using, sort of easily visualizing where this this custom vector is. So we're going to go up one level, and now we're back into subs, and I'm going to lay down an add. So I'm going to add a point. I'm going to get rid of this guy. I'm going to enable this point, and the point that I want to add, if I just look at it, at the moment is at the origin. Let's say we want to put it up a little bit, so now it's sort of 10 units up in Y, and I'm going to put it just a little bit of an offset there, and now it's like 2 units in X and 10 units in Y, and I'm gonna plug it into this into the first context. It's not necessary, but it kind of indicates the sort of relationship. Gonna name it like add custom vector. So I know that this is one that I'll be using inside of my popnet. So I'm going to dive back, and now I'm going to create my custom vector using a new attribute. So lay down a new attribute, and I'm going to call this one custom vector. This will be sort of our backup vector in case the other one fails, and I'm going to try to keep it short, so cvec. Gonna name it cvec. It's kind of convenient to at least I find it convenient to put like the name of my attribute into the name of my parameter at the end, so I can easily know like, okay, dot product dp custom vector, cvec. Okay, so it is a vector. Alright, what kind of vector is it? Now I need to kind of go and get it using an expression. So the expression I'm using is a point expression. So I have to go up. I have to go up to the point level. So dot dot. So at the moment I'm in pops. I have to go up once more. Dot dot slash. And the one that I want is there, add custom vector. Okay, the point expression has got sort of 4 arguments. So the first argument is a path, as you can see there, string, float, string, float. The second argument is which point number to apply it to. So what I want to get is $pt. And this string will basically tell me which attribute. So the attribute that I want is the position. So I want p, this is position. And then the last float indicates which component of that attribute. So this attribute, this position, for that point, is basically going to be 0, 1, or 2, which basically will give me the x component of the position, the y, and the z. So I'm currently into the x, so what I want is z. So sorry, 0. Okay. So this will give me the x component of my custom vector, which I added in subs, which, if I remember, was 2. So if I evaluate this, this should give me 2. So let's copy this entire thing, and now let's do it for y and z. So this is for y. So the only thing I need to change is there a 1, so the index, change it to 1. And the only thing in z that I need to change is again the index, change that to 2. Okay, if I look at my values, it's 2, 10, and 0. So my custom vector is now, correctly being referenced. Okay, now the big thing. Let's start to calculate our cross product, and let's start to use, sort of the correct cross product as it goes. I'm just going to save it quickly as well at this point.